just kind of wanted to review the inverse functions before we get to the properties of log today. So let's do a quick review problem, writing an inverse function of a logarithmic function. And then what I'm going to ask you to do is I'm going to ask you to submit a short classwork problem that looks just like this. Mine is log base 2x plus 3 minus 1. The one that you're going to try for me for the review of inverse functions problem, the one I'm gonna make sure that I'm not doing the exact same problem. I don't think I can open it on my what's it called, iPad. So you're gonna have to be on your computer to open it, or maybe your cell phone to open it, or maybe I can just type this problem on Canvas for you so that you guys can open it on your device. Okay, because I just learned that a PDF, I cannot open it on my iPad if I just include it as a PDF document on this Canvas. But just want to make sure that I'm not doing the exact same problem. So I am opening this while I'm talking. I'm opening this on my laptop right now. And looks like the problem looks slightly different. So, okay, I'll go over this one. But then the one that you're going to try for me for your classwork is this. Classwork problem is g of x equals log of x minus 3 plus 5. Now, a good question you may ask is, what is the base, right? Because you're going to need to use the base to write the function, or the exponential function. But if you take a look, my base is 2. My base is 2. But what is your base if it's not written? Notice that's common log, right? So for common log, what is the base? So I'm going to ask you to try that problem, but I'm about to do something very similar, and I will also review domain and range. I'm thinking about cutting this video in about like 2 pieces instead of just recording a long one. So I plan on doing page 1, maybe page 2, and some problems on page 3, because the later ones are a little bit more complicated. So I'll come back and do those, but I did want you to do a quick review problem. Okay, all right, let's try this one. Find the inverse function and state the domain and range of f of x and f inverse of x. So we do know how to find the inverse function, so let's start with that first. So first change your f of x to y. Y equals log base 2 of x plus 3 minus 1. So step number 1 is just changing the name f of x to y. And we did that. All right, now we are going to switch x and y. So instead of y equals, you're going to have x equals log base 2 of y plus 3 minus 1. So that's step number 2. All right, now step 3 will take some time. We have to solve this for y, right? Now we have to solve for y. So first thing that we can do is we can add 1 to both sides. Notice we can add 1 to both sides, plus 1 and plus 1. Let me write down what we have after that. Then we're going to have x plus 1 equals log base 2 of y plus 3. And we know that we are not allowed to subtract 3 from both sides because what? Y plus 3 are the arguments of this log expression. So you cannot subtract 3 here. Okay? So what we're going to do is, here, let me write it down. We're going to rewrite in exponential form. You will have to do that step when you're going from a log function to its inverse function. Notice, remember, they're inverse of each other. So if I'm writing this as an inverse function, what is the base? The base is 2. So you'll write this as 2 raised to the x plus first power. That was from the other side of that equal sign, right? And that equals what? That equals y plus 3. Okay? Now that step is going to be the hardest. But now we're going to just have to solve for y. Subtract 3 from both sides. And let me switch the left and right side and say y equals 2 raised to the x plus 1. But notice I'm subtracting 3 after, so the only exponent part, that's the power, okay? 2 raised to the x plus 1, but then write that minus 3 big. It's not part of the exponent, okay? So let's give that fancy inverse notation. F inverse of x equals 2 to the x plus first power, but it's going to have a vertical shift of 3. So we found the inverse function. So I want you to highlight that or circle that so that I can check your answer. But make sure you show the work to get there, okay? Now let's talk about the domain and range. You really have to just find the domain and range for one of them, and the domain and range for the inverse will just be switched, right? Now, remember, it's a good review again. Let's talk about the domain of a log function. Domain of logarithmic function. I kind of gave it to you as a rule, but you do know the domain of a log function depends on the horizontal translation. Notice this graph is shifted 3 to the left, right? Well, but I did give you a rule. You do say argument is greater than 0. That's what you're gonna have to do, because remember, in a parent log function, you do have a horizontal asymptote. I'm sorry, it shouldn't say horizontal. A vertical asymptote at x equals 0. So what we're gonna do is we're gonna grab this argument, that inside part of the log, and you're gonna set it greater than 0. Do not say greater than or equal to. It cannot be 0. If you solve this, you will get x has to be greater than -3. And if you write that as an interval notation, then the domain of this log function is anything greater than -3, all the way up to positive infinity. Now look, that's the domain of the original f of x. Then the inverse function must have a range of the same exact thing. So once I know the domain of this f of x, I do know that the range must be exactly the same. Okay? All right. Now, remember, the log functions, they do have this tail going down. I mean, I'm thinking about the graph of it. But the easier way to remember the range of a log function is just kind of what is the domain of an exponential function. Remember, that one is always all real, right? Why? Because we can raise 2 to the any power if we want. We can raise 2 to the 0 power, 2 to the negative power, 2 to the decimal or fraction power. So domain of an exponential function, we don't really have a restriction. We can have any number. So remember, automatically, well, we do know that the range of an exponential function, range of a logarithmic function is going to be -infinity to positive infinity. So I want you to try something like this. Mine was base 2 log, right? What is your base? Your base is 10, but I know you knew that. Okay, so you're really ready for this review problem. Just wanted to kind of give you a quick one because you've been doing classwork on Canvas quiz or quizzes for me, but I did want to see your handwritten work. So just do this quick one for me, but then let's go ahead and start 3.4, properties of logarithms, okay? All right, the first one is pretty easy. It's called change of base formula. And for some of us that does have a calculator that can compute a log base other than 10 or e, we really don't need this change of base formula because our calculator can find it. But any scientific calculator or a small calculator that doesn't have the log base, this will be very useful. So you will be able to calculate something like this. Let me write up an example, okay? You may get something like log base 3 of, let's say, 50. I'm just making it up. Okay? Now, let me show you how I can type this into my scientific calculator that I downloaded, which has the log base button. Okay. Go to log base, or in your math, what's it called? TI-84, you may have to go to math, and probably like option A, the log base. I'm going to type in the 3 for the base and then 50 for the argument, and I will get the answer to be approximately 3.56-ish, right? Now, here's the thing though. I want to show you that you don't have to have that log base function in your calculator. So the change of base formula states that you can evaluate any log if you just rewrite it as a quotient of two separate logs. So what you can do is this. You can pick either common log or natural log, up to you. But you can do common log. You can do log 50. Guess where I got that 50 from? Divided by log, what number do you think? 3. If you type that in, you will get the same exact number. So let me show you. Log 50. I'm going to do log 50. Because everybody have log button on their calculator. Divided by log what? 3. And if I hit enter, I will get the same exact decimal, 3.56, right? But it's not just going to be log. You can use natural log too. So take a look. I'm going to type in natural log of 50 divided by natural log of 3. I better get the exact same decimal, 3.56. That's what the change of base formula is talking about. So now, oh, hold on. Let me see if I can write down, squeeze in that ln 50 divided by ln 3 here. Kind of cool formula, right? Because in case you don't have one of those fancy scientific calculator or the graphing calculator that doesn't have a log base, then you can just make it a division of two separate logs and then still evaluate it. So that's what this is talking about. So let me go ahead and go over a couple examples using that property, okay? So use the change of base formula to compute A through C. Round your answer to the nearest thousandth. Now, I know some of you have that scientific or graphing calculator that does handle this, but I'm going to use my log base formula. I like natural log. I'm going to do natural log of 7 and divide it by what? Natural log of 2. But what if you want to do the other one? Can you do log 7, common log 7 divided by common log 2? Yes, it doesn't matter which one you type in. You will get the same exact answer anyways, okay? You just don't want to mix them. You don't want to put ln on top and log in the bottom, okay? All right, let me go and type these in to my calculator. Clear. Let me do natural log of... Oh gosh, guys, I forgot what the numbers were. Sorry. Got my numbers. 7 and 2. My pregnancy brain, guys. All right, back to the calculator. ln 7 divided by natural log of 2. I'm going to hit enter. The answer is 2.807. Now, just want to show you that if you even do common log of 7 divided by common log of 2, guess what decimal you're going to get? The exact same decimal. So, let's go ahead and write these down on our notes. This answer is approximately 2. They wanted you to round to the nearest thousandth. So I'm going to give them 807. And you saw how this one was also 2.807. So up to you if you like natural log. If you like natural log, then you use your ln. If you like common log, then you can use log. Don't have to do both of them. All right, let me do B and C, okay? B. Well, this time we have log base 5 of 2/3. I'm going to do natural log of 2/3. And I will divide that by natural log of what? 5. All right, let's see what that is. Going to my calculator. Natural log of 2/3 divided by natural log of 5. All right, the answer is negative 0.25. I'm going to round that 9 up to 2. So we got the answer to be negative 0.252. But if you want to know if that's really correct, and if you happen to have a calculator that will do log base, then I can check it too. I can type in log base. 5 was the base, right? And then the 2/3 was the argument. If I hit enter, I get the same exact decimal. So this change base formula really works. All right, back to the last one. This time, I'm going to do the common log. Why not? Just mix it up. I'm going to do log of 1/7 divided by what? Log of 1. Oh, no. Oh, okay. No. Not 1. What's the base? 1/6. 1/6. I thought I had a an interesting problem, but well, I'll just do it. Alrighty, let me go back to my calculator to type this in. Where are you? I will do log 1 over 7 divided by log 1 over 6. And if I hit enter, I got the answer to be 1.086. Just out of curiosity, if I go with the other guy, the natural log of 1 over 7 divided by natural log of 1 over 6, you will see that we get the exact same decimal. So I think that's enough for the change of base formula, 1.086. Now let's go over something a little more exciting, okay? On the product property of logarithm. Okay, we're now on product property of logarithm. And then we may be able to do the quotient property, and then I'll come back and maybe finish page 4 and 5, okay? All right, the product property. Where are you? Product property of logarithm. Looks kind of confusing with the numbers, but let me go ahead and show you what this is really. Say that you have a log base, whatever, like 3. I just made up a random number. And then you have, I'm just going to give you a random number of 7. And then you have plus log base 3. Say that you got 5 in there. You can combine these two logs. First of all, they must have the common base. Do they have common base? Yes, their bases are both 3. If they have the common base, what you can do is you can combine them and write this as a single log base 3. But then the product property is talking about what you do with the arguments. You see that you have a 7 here? And we have a 5 for the other argument. When you are adding these common base logs, what you can do is you can find the product of their argument. So I will do 7 times 5 and get 35. And now, you're wondering, how does that rule work? But remember, log and exponents are closely related. So you may have seen something like this before. You may have seen x to the 3rd power times x squared, right? And now, what's the answer to that? If you simplify that, will you get x to the 6th power or x to the 5th power? Well, that means we have 3 x's here, 1, 2, 3 here. And then we have how many x's here? 2 x's here. So that turns into x to the 5th power. Notice when we were multiplying the exponents, power expressions, we actually added these exponents. So you kind of saw this cool rule before, but now we're doing the log property. So when you are adding the common base logs, what you get to do is you get to multiply the arguments together to write it as a single log, okay? So this 35 is from 7 times 5. But then the restriction is they better have the common base. Okay, so let me try a couple problems down here for you. Write the expression as a single logarithm. Okay, notice I better first see if they have the common base. That's log base 2, right? And that's log base 2. Now, they have the same log base, so I know I can combine these two. Log base 2 of what? Now, once they have the common base, you check and see that they're adding in the middle. So what do you do with these arguments of 3 and 4? You multiply 3 and 4 and you get 12. Therefore, the answer is log base 2 of 12. Okay? I'm going to make these a little more complicated for you a little bit later. But I guess these are just values. So if you want to check if the left side really equals the right side, you can type log base 2 of 3 plus log base 2 of 4 and check and see if that's really equal to log base 2 of 12. Let's do that just because. All right, let me go ahead and type in the original problem, okay? The original problem was log base 2 of 3. And we were adding log base 2 of what number? 4. And that was approximately 3.5849, okay? Now, I'm going to go ahead and type in what I got using the property. What is log base 2 of 12? And remember, we got the 12 from multiplying 3 times 4. If you hit enter, ta-da, the exact same decimal. So if you're just brand new to this property of logarithms, why not? Double check your answers because you have that technology, right? So that's what we can do. Ooh, look at all that extra room I have. I really didn't need all that extra room. All right, let me do another one down here. B. Now I got log base 5 of 4x, and I got log base 5 of 2x plus 1. Once they have the common log base, I know that I can combine them. Log base 5 of. Now, what do we do with the arguments? Because, well, if you're adding the common log bases, we're not adding these arguments. Remember, we're multiplying the 4x times, what's the other argument? 2x plus 1. So what we can do is at least we can try to distribute that. Why not? Yeah. So the final answer that I will probably leave is log base 5 of 8x squared plus 4x. Okay? That's what we can do. And unfortunately, this one I won't be able to check the value because we don't know what x is. But I guess if you can just plug in a random x, that's going to keep your argument positive. This is okay for you to check on calculator, but that's the product property of logarithm. So remember, sum of the logarithms will turn into, then you're gonna have to find the product of these arguments to combine them or condense into a single log, okay? So if adding turns into multiplication, what do you think subtracting will turn into? And the answer is going to be division, right? So take a look. I'm going to go ahead and write down something like this. What if you have log base 6, just random, log base 6 of, I'll do the other way around, log base 6 of 15 minus log base 6 of, let's say, 5. Let's combine these two, okay? First of all, you check and see if they have the common base. Both of their bases are 6. Then you get to combine them and say log base 6 of. Now notice this is subtracting in the middle, right? If you have subtracting in the middle, you're not going to multiply the arguments. You're going to divide the arguments. So if you do 15 divided by 5, this actually turns into log base 6 of what number? 3. So you can do it that way. That is the quotient property of logarithms. So let's use that property down on A and B here. So we're going to write as a single logarithm. The condition is that they must have the common base. Now let me see. This is ln. This is natural log. They're both natural log. Their bases are both e. So we get to combine them. Yay. So I will say big 1 single natural log of. Now let's see. Notice they are subtracting in the middle. So we're going to divide the first argument, 12x squared, by the second argument of 4x. Okay, so if it's subtracting in the middle, you divide them. Okay, so I get to simplify this. Natural log of 12 divided by 4 will give me 3. X squared divided by x will give me x. Therefore, the final answer is going to be natural log of 3x. Okay? Ooh, look at B. It's not only subtracting, but you notice we got an adding there, and then we got a subtracting there. Okay. So let's do this one together. But first of all, the condition is that they must have all common log bases. This is just log, this is just log, and this is just log. They're all common log. What's the base? Base is 10. So we get to combine them into a single log, single common log. Now notice that I'm going to do 6x times y, right? I'm going to do 6x times y. I'm multiplying these two because they're connected by an adding sign, right? Now what's next? The next one is getting divided by. So I'm going to divide these by 3z. The third argument is 3z, but we're dividing by it. So if you can try to, well, the answer is this, but if I can just try to write it a little bit smaller, that is log of 6xy over 3z. Whenever you're subtracting, that argument just goes straight to the bottom of that fraction. But we'll see more and more of these together because I'm going to start giving you some of the more complicated looking examples down here. Now, but you just looked at the product property and the quotient property. The third basic property is called power property, and this is pretty fun. Say that you have something like log base 3 of 5 squared. What you can do to the square is you can bring it down in front of it and say that's equivalent to 2 times log base 3 of 5. Okay, that's what you can do. Sometimes you can go backward too. What if you have 1/2? Let's say that you have this fun 1/2 natural log of say 9, okay? See what that is equal to. Now, this exponent, well, this fraction in front of it can go back to the exponent of the argument. So what you can say is this is the same thing as natural log of 9 raised to the 1/2 power. But what is same thing as raising something to the 1/2 power? That's really taking square root. So we're looking at natural log of 3 here. So let's confirm this on our calculator. I am telling you that 1/2 of natural log of 9 equals natural log of 3. So I'm going to go ahead and type this and show you that this is really true. So typing in 1/2, oh, where did my fractions go? Oh, 1/2 times natural log of 9. If I hit enter, I get 1.098. But this time, let me type in natural log of simply 3. Ta-da! You see how it's exactly the same decimal? So that works. You can pull the number back to the exponent and write it that way. And just depending on which way I want you to go. So let's go ahead and try this. They want you to write the expression as single logarithm. Now we're talking about some fun stuff. After these 2 examples, I will stop the video and then I'll come back and show you where we put all these together on page 4 and page 5. Okay, because after this, these 2, you'll be able to get the basic properties and we're just going to have to apply them to solve a little more complicated looking problems. All right, let's do this one. This does look complicated though. All right, anyways, I see all these numbers in front of it. What I'm going to do is I'm going to make a little indication that these exponents are going, the coefficients are turning into the exponents of these terms. Okay, so that's my first step. I'm going to do that first. So first I get log base 3 of x to the what power? X to the 5th power. Write it small. Write it so that it looks like a superscript. Okay, minus log base 3 of y minus 1 to the what power? 1/2 power. And then plus log base 3 of w to the 2nd power, right? So the first thing that we do is we just send all these coefficients back to the exponent's position, okay? All right, let's see if we can combine them, because if they all have the common base, we can write them as a single log, and they all have a base of 3. So let's write it. Log base 3 of, it's going to be a fraction. You know why we know that it's going to be a fraction? We got a minus there. So whatever that has a positive sign in front, it's going to stay on top. X to the 5th. Notice it was a positive x to the 5th. It's going to be on top. But I'm going to draw the denominator of fraction bar and put this y minus 1 to the 1/2 power in the denominator. Why does that go to the denominator? Because we're subtracting. And when we're subtracting common base log, we make them into a quotient. And now this one, the very last one. Where do you think this w squared will go? That one will go to the numerator. And the reason is because w squared has... this term has what sign in front? This one has a positive sign in front, so it needs to stay on top. Now, this is a fine-looking answer, but if you want to simplify this or if you want to just rewrite it, I guess one way of doing this is this. You can leave it as x to the 5th times w squared, but you can make the denominator y minus 1 square rooted, okay? Up to you. Both, for me, are looking fine, but we used not only the power property, but we also use the product property and quotient property to do this problem. All right, let's do one more. I'll just make it a little bit smaller over here. Okay, now this time I have, look at this. This 3 is in front of both of them. Of course, there are better ways to do different things, but I'm just going to go ahead and distribute this 3 to these 2 log expressions so that they're separated, not in a parenthesis anymore. So let me go ahead and write this as 3 times log base 4 of x minus, not anymore 2 though, right? It's going to be, what? 6 times log base 4 of y, and then plus 2 times log base 4 of w. Okay, so what I did, I just distributed that 3 to these 2 terms inside the parenthesis. Now, notice we have coefficients in front of these log terms. So we're going to send this 3 to the numerator, exponent, this 6 and this 2, and then rewrite it So I'll have log base 4 of x to the third power minus log base 4 of y to the sixth power. And lastly, log base 4 of w squared. Okay, now as I was writing it, I checked it. They all have base 4. So that means we're allowed to put them as a single logarithm with base 4. All right, notice we have a minus sign right there. So we're going to have a fraction. X cubed will stay on top, but we're going to send y to the sixth power in the bottom. And this w squared will be on the numerator because we're adding. That's going to be multiplying. So that's it. Nothing else to simplify there. 4 and 5 are really the same things, but just kind of, I made them fun. Like kind of, hey, find the missing value using these properties. But these may take a little bit longer time, and I try to have a video. I try to keep these videos less than like too long, because sometimes if they're too long, it takes forever to process on YouTube. So I will come back and go over page 4 and 5. But if you want to take a quick break and try that review problem where you have to write the logarithm log function into the exponential function, the inverse function problem, feel free to do that and submit that by this Sunday for me, okay? But I will be back with the second video going